Okay, in this item we get the wonderful opportunity to deal with shapes that are best described not by maybe special geometry but by equations. And how do we deal with that? It's going to be the continuous world of what before we were dealing with discrete objects, except for anything that we have that's continuous could probably be thought of in some sort of composite-like behavior, and doggone it, that's what we're going to do. Because here's the deal. If we're going to deal with a continuous world, the discrete one says that, for instance, say we want to find the centroidal location of the shaded area with respect to the x-axis. There's our datum. Hey, that in the discrete world we'd say x bar is equal to the sum of the composite areas. Oops, sorry, we want it from the x-axis, so that's by bar. Would be the sum of the y bar a first moments of all the compositive areas divided by the total area. Right? Well, the continuous version of that is to say that y bar is equal to the integral of some centroidal moment of area times the differential area divided by the total. What the heck am I talking about? Well, we have to start coming up with differential strips. This is calculus. And we all know how much engineers seem to love calculus. We all seem to be very afraid of it. Right? So we're going to take a little tiny differential strip. That's going to be dx wide, right? And it's going to have a height that is, well, let's take that one as y, actually we're going to take that one as y2, and we'll take the bottom one as y1, and so the height of that differential strip is y2 minus y1. Any wonder why engineers don't like the math? And then you got to find the centroid of that little rectangle, which is going to be right there. That's y sub c. And y sub c, in this case, would be equal to the average of y1 and y2. Oh, my goodness. Right? We're already getting ill. Wait a minute, what? The difference in the height is y2 minus 1, and then y sub c is at the average of those two. Oh my gosh. Right? Well, that looks like we're starting to set up a lot of really hard work. So let's keep plugging away a little bit, and then we're going to look at maybe a slightly different way of handling this. So, okay, we're going to do that first moment of area respect to the x-axis. That's the integral of ycdA, and that is going to be y2 plus y1 divided by 2. That's our y sub c times the dA. It's a rectangle, so it's got a height of y2 minus y1, and it's got a width of dx, and then that would be, yeah, that's right, that would be y2 squared minus y1 squared all over 2 times dx, and then we got to substitute in for y2, which is equal to mx, so that's m squared x squared minus then k squared x to the fourth all over 2 dx, and now that'll go from 0 to a, and we got to evaluate all that. Oh my gosh, right? That's how a lot of people will think about it. They don't like doing all that work. It's actually not too bad, but it's still a lot of work to do. So another approach that you could do is you could look at this area as the sum of two. It could be the triangle that has a base of a and a height of h minus then this special parabola. It's called a spandrel. It's tangent here, and it's only got one second order term in here. It also has the same base and height, h and a. Right? And that's y equals kx squared. Well, we know on the first one, for instance, the m is equal to the slope, that's h over a. And if we come out to here, then we'll find out and solve for k that k is equal to h over a squared. Right? That's how that would all play out. Right, now we could do this. This is a composite area. Now we got to deal with, well, we still have to find the first moments and the areas and all that kind of stuff. Now this one, check it out. That one we of course know its area is equal to 1/2 of the base times the height. This one, if you integrate this and evaluate it here, you should find out, and I challenge you to do it, that that will be 1/3 of the base times the height. There is a very special relationship that's happening. We've gone up by order in the polynomial from x to the first to x squared. We got the same base, same height. We've got the vertex over here, and that went up by 1. If this was a cubic function through there, that would be ah/4, it turns out. And there's a very nice, pretty relationship that happens here. That would give us here the total area, which is going to be 1/6 of the base times the height. 1/2 minus 1/3. That's the area. Now, how would we find out then the centroid of this little segment here? Right now, we're going to prove what you can find in property tables. There's our little guy, right? Has height of y, right? So height of y, so the dA equals y times dx. Its centroidal distance is at half of that height, y/2. And y is equal to, of course, mx. Right? So that means the integral of yc dA. So if we add up all the first moments of the differential areas, then we'll have the integral of y sub c was equal to y/2. Of course, dA was equal to y times dx. So that's y squared over 2. Now y equals mx. So that's the same thing as m squared x squared over 2. Integrate all those from 0 to a. And so that'll be m squared x cubed over 2, evaluated from 0 to a. M itself is h over a, so that's h squared over a squared. And it looks to me like I dropped off the 3 on the integral, right? And so that's over 6, evaluated there, that's a cubed. So that's going to be h squared a over 6 for the first moment of area of that triangle, right? So then, of course, we find the y bar for the triangle is equal to this first moment divided by the total area, so that's h squared over a divided by 6, and then divide by the area, which is 1/2 the base height, and take the reciprocal of that, so that's 1/2 of base times height, and look what we get here. The a's cancel out, 2 over 6 is 3, and we have h squared over h, that's just h over 3. So the centroidal distance for the triangle is at the 1/3, 2/3 location. 1/3 towards the big end, 2/3 away from the skinny end. Right? Same thing would be true with this right triangle going left right, 1/3, 2/3 of the base sitting out there someplace. Huh, that's kind of interesting. Hey, let's do the same thing for the parabola. Did I go off screen there? Sorry about that. Hope you can follow, get a snapshot of where we're at. Now we're back in shape there where you can see that. Alright. Hey, goofball, you're off the screen. I wish you were here. Alright, so we've got kind of the same thing, right? It's still the same differential strip, although its magnitude is different, right? We're still going to go y/2, that's half the height of the rectangle, and then times y dx. A lot easier to work with than this big mess that we had up in here. And so that's y squared over, but y squared is, y is a different function. We're going to get k squared x to the 4th over 2, integrating then from 0 to a. And, oh, alright, so k we found was h over a squared. Now we got an h, or a k squared, so that means we've got h squared over a to the 4th. There's a 1/2. X gets integrated from x to the 4th to x to the 5th divided by 5. Evaluate from 0 to a. And we're going to get an h squared over 10, a 5th over a 4th, so that's just a. Huh. Interesting. Now I'm not going to work out the area. Oh yeah, I already did work out that. I told you what the answer was for the area here. So the y bar for the parabola then is going to be the first moment, then divided by the area, which was 1/3 of the base times the height. And so we get a here, and the h goes away, and we get 3/10 of h. h for that height. That's kind of interesting. Now that's not the same thing of the horizontal centroidal. That's going to turn out to be the 1/4, 3/4 business. 1/4 from the big end, 3/4 of the base going the other. Prove it. Right? Set of tables. So it's not the quite same thing as what we got going with the triangle, but very similar. Okay, now we can put all this together if we want. Right? So now we can do same business that we have done before, and that is that we've got to take the first moment of the big stuff, the positive stuff. That first moment is h squared a over 6 minus the first moment that we have from the negative area, all divided by the net area, ah over 6, and that is our y bar, right? This is now applying the discrete version, sum of the first moments of the individual areas. And when we simplify that, we're going to find out that that's 2/5 of h, right? The a goes away, we got h squares divided by an h. This is going to turn out to be 1/6 minus 1/10 is 1/15. 6 over 15 is the same thing as 2/5 h. Kind of interesting, right? So that might be a lot to absorb. It was sort of twice as much work, but we didn't have to go through all this. We could have. It would have been okay to do. But the key in all situations here is setting up this differential area, identifying where your centroid is of the differential strip, getting that formula right, which is not easy. In fact, I did this wrong the first time I did this, and so I had to redo it because I did it two ways. I did it this way, didn't get the same answer as I did this way, and I was confident of this one, so I finally figured out the mistake I made. But wow, it's a lot of calculus. Yeah, it is. That's why engineers love it so much.